Okay, we made it to Module 9, and Module 9 actually covers two chapters. We have chapters 26 and chapter 27. Notice in chapter 26, one of the main ideas that is covered is the structure of the Earth's interior, which is actually rather mysterious. You know, we've explored space, we've gone to other planets, and yet we've barely scratched the surface when it comes to literally, when it comes to actually discovering stuff inside our own Earth. It's really tough to drill down inside the Earth. So what we know of the Earth and the Earth's interior structure largely comes from seismic waves. So you'll notice there's a lot of detail early on in the chapter 26 about seismic waves, and then it gets into how rock can deform and fold and fault and that sort of stuff, which kind of makes up the majority of chapter 26. Chapter 26 also gets into earthquakes, and actually up here there's a video of a earthquake awareness session that one of the other ICC instructors, Mr. Brady Garrett, and I did. We went to a couple of summers ago at the University of Missouri. We went to a workshop called The Dynamics of Intraplate and Other Earthquakes, because we are not that far away from the New Madrid earthquake zone in the boot heel of Missouri. The New Madrid earthquake occurred over 200 years ago, and it's unlike the earthquakes that we usually think about. We usually think about earthquakes being out in California, where they're close to plate boundaries. We're not at a plate boundary, and yet there can be earthquakes even in the middle of a plate. Those are called intraplate earthquakes. And if it were to happen today, it would be a whole different story than it was 200 years ago, when the Memphis area wasn't really that developed. Now, there could be millions of folks affected by a similar strong earthquake like the New Madrid earthquakes. So anyway, check out that video if you want to learn more about the New Madrid fault zone. And of course, if you want to learn about chapters 26 and 27, keep watching this video.
She's going to tell us a little bit more about the program. And also talk to us about different
called nodes. So if I touch there, there's not even sharp string really. If I touch here, it flattens out.
This arc is small. It was transformed from an area that was of some utility according to
Energy brings showed up there and it was transmitted to solid bedrock.
So development actually early education. Okay. Come out and see Mitzi Ward and find out more about this program.
Thank you very much. The earthquakes occurred in southeastern Missouri. He was woken up in Washington, D.C. 1,500 miles away. Who was it? Correct answer. James Madison. Next question. What was the population of St. Louis at the time of the earthquake?
2 year program. Thanks so much, Jody. Y'all come by and check it out.
So we begin our study of chapter 26 by talking about seismic waves, and kind of like sound waves. You know, what are sound waves? Sound waves are just ways of transmitting energy from my vocal cords to your eardrums. And you need a medium, you need air, you need water, you need some sort of a medium to take that energy from my vocal cords to your eardrums. Same thing, seismic waves are just a way of carrying energy through the earth. And by using seismic waves, either through earthquakes or artificial earthquakes, we've learned a lot about the structure of the Earth's interior. So it turns out the Earth's interior is not just all one type of stuff. It turns out that it actually has layers, kind of like a jawbreaker, where it's got an inner core way in here, it's got an outer core, it's got a mantle, and then it's got the crust. So notice the crust is very, very thin. These other layers are much, much more significant. Overall, if you were to start digging from wherever you're at to the center of the Earth, you'd have to dig about 4,000 miles, essentially, for 6,300 kilometers. That's how far you'd have to dig just to get to the center of the Earth. So, and in doing so, you'd pass through several different layers. Now, when we talk about seismic waves, it turns out there are different types of seismic waves. There are what are called body waves. Those travel through the Earth's interior, and those can be described as either P waves, primary waves, or S waves, secondary waves. There are also seismic waves that travel on the surface of the Earth, and those can be differentiated into love waves and Rayleigh waves, and these are the ones that actually do most of the damage in an earthquake, because of course most of the damage occurs at the Earth's surface. To help you are getting into the habit of doing these explore activities, check out the explore activity on page 616 at the beginning of chapter 26. And it's about waves, but it helps you to differentiate between what are called longitudinal waves and transverse waves. Now they call for a slinky. I don't actually have a slinky here in my office, but I've got a phone cord. And so a longitudinal wave, this is what primary waves are. Remember, the body waves that go through the Earth can be broken into P waves and S waves. Primary wave are longitudinal waves, which means that the energy is in the direction of the wave motion. So if I do one of these jobs, I can send a blast of energy down through my slinky, and it comes back. Right? It heads in the same direction as the original displacement. So that is a P wave, and it turns out that P waves are the fastest traveling waves, and they actually can travel through any type of medium, any type of material. S waves, secondary waves, they travel in a different way. They travel like if you shake your slinky from side to side. You'll see that if you just give it one pulse to the side, a wave will go down the slinky and back up the slinky. So the motion, the excitation is in this direction to the side, and yet the wave travels in that direction. That's what's called a transverse wave, and that's what secondary waves are. They're slower, and they also don't travel through liquids. They only travel through solids. So that's really important because that helps to flesh out the different the nature of the different layers of the Earth. So some are solid and some are liquid, and you can tell the difference by telling whether primary waves go through them or whether secondary waves, whether both, etc., etc. Okay, so we've already talked about the relative speed of primary waves versus versus secondary waves. Those are both body waves. Surface waves are the slowest of the bunch, so they actually show up last on a seismograph. And as described, Rayleigh waves are kind of like ocean waves, whereas love waves are kind of side-to-side horizontal waves. Just like sound waves travel at different speeds depending on the material they're traveling through, same thing with seismic waves, and that's really important and useful in determining the density and the structure of the Earth's interior. You can learn about the different materials that make up the Earth's interior by studying the speed of the different waves. And of course, different scientists have done a lot of these studies in the past. So the next several slides actually detail the dates and who did what and all that kind of stuff. Some of the stuff is in your book, some of the stuff is actually supplementary to your book. One major discovery was made by a guy named Andrija Mohorovičić, and he discovered that there's a boundary, a sharp increase in velocity between the crust and the mantle. And it's something called the Mohorovičić discontinuity, usually just called the MOHO. But that was discovered in the early 20th century. Again, by measuring the relative speeds of the different types of seismic waves, as well as whether or not they even pass through. So notice here, you can see that certain waves pass through. These are primary waves that are able to pass through. And notice there's a shadow zone. That indicates that there is indeed different densities of materials as you go into the Earth. And so it actually creates a shadow zone where there are no waves. That's called a P wave shadow zone. And so by noticing these shadow zones, by noticing when S waves don't pass through at all, the interior of the Earth's structure was essentially teased out, which again is very cool. We're probably never going to be able to drill deep enough to sample the center of the Earth, literally sample it, send a probe down or something like that. But we can use seismic waves in order to essentially indicate and to detail the structure of the Earth's interior. So we know the core is solid and made of predominantly metallic iron. There's also some nickel there as well. And these are metals, as we've talked about. Remember what metals have. Metals have a lot of free electrons. And so you got a lot of free electrons, negative charges, that are spinning. And think about how fast the Earth spins. It spins once on its axis every day, which means that the equator moves about 1,000 miles per hour. And so you have electrons that are moving very quickly, and therefore, anytime you have fast-moving charged particles, you wind up getting a magnetic field. So the Earth's outer core actually produces Earth's magnetic field. Now the next several slides detail essentially the different layers. So the mantle is made up of different parts, and this is really an important part. This asthenosphere, the upper mantle, it says it's plastic. That does not mean it's made of the materials that make up toys and stuff. What it means is that it is rock that is so hot and at such pressures that it actually can flow. So that's what plastic means in a geological sense. And so we have the asthenosphere, we have the lithosphere, and essentially the lithosphere is going to make up what we call the tectonic plates that we're going to study in chapter 27. And these tectonic plates float on top of the asthenosphere. So as we already mentioned, the upper mantle essentially can be divided into the asthenosphere and the lithosphere. The asthenosphere is that plastic flowing material. Lithosphere is the crust, and it's essentially solid, but also broken up into plates. Tectonic plates are very, very important. It's actually the focus of chapter 27 material, because without knowing about plate tectonics, we can explain earthquakes and volcanoes and that sort of thing. The lower mantle, okay, so we've already been talking about the upper mantle. The lower mantle is at great pressure, so therefore it is considered to be a solid. The crust is actually, we talked about the lithosphere, the crust. You have two different types of crust: oceanic crust and continental crust. Oceanic crust, much, much thinner. Continental crust, much thicker. And that has that's important when you have collisions of oceanic type plates against continental plates. Okay, now's a good time to catch our breath and try a skills test. And in this skills test, you're actually going to watch a video and then answer some questions about seismic waves and how, again, the structure of the Earth's interior is kind of pieced together by using information from seismic waves. It is admittedly kind of weird to think about the Earth's crust as floating on something, but it is. This asthenosphere that we talked about, this plastic flowing rock below the lithosphere, essentially acts like a pool of water. So just like a block of wood would float lower in the water than, say, a beach ball. And the reason being, there are different densities, right? The beach ball is less dense than the block of wood. In a similar way, continental crust is less dense than oceanic crust, and therefore the oceanic crust kind of floats lower in the asthenosphere than the continental crust does. Notice we're going to actually take a little jump ahead into chapter 27. Before we get into earthquakes, which is the end of chapter 26, we're going to move ahead into chapter 27 and talk about continental drift. Because continental drift is a really interesting scientific theory, and it kind of it shows the scientific method at work. And so essentially what continental drift, the hypothesis was, and it was developed by a guy named Alfred Wegener, but he noticed some things. He noticed that the continents sort of fit like puzzle pieces. He thought, gosh, that's sort of interesting. He proposed that the continents weren't just in their present positions and for all time. He thought that because of the sort of interlocking shapes that they must have moved around in the past, and perhaps are still moving presently. Which that's an interesting hypothesis, but just that piece of evidence alone, the fact that the shapes are kind of like puzzle pieces, may not be quite enough. So what he did was he started to look for other evidence, and he started to find it. So he was able to back up his hypothesis by gathering new evidence, and the new evidence being matching rock types. The rock layers, the layering was similar. From a rock outcrop in South America might match a rock outcrop in Africa. indicating that, so if you had a rock outcropping that was very similar in layer structure to one over here, that would make sense that at one time these continents were joined and have since become separated. He also was able to use fossils. He was able to find fossils in South America that were similar to fossils in Africa, et cetera, et cetera. So he had a lot more supporting evidence for his hypothesis. One of the problems was he couldn't identify a mechanism. He didn't know why the continents were moving. He had evidence that the continents had moved, but had no evidence as to why, and that was really interesting. So this is very similar to in astronomy. Johannes Kepler is well known for Kepler's laws of planetary motion. He was able to describe how the planets move. They move in ellipses, nearly circular, but not perfectly circular orbits. And he was able to come up with laws about how the planets move. He didn't know why the planets moved. It wasn't until Newton came around and came up with his law of gravity. That explained the mechanism that drove the motion of the planets. In a similar way, Wegener, he knew that the continents were moving, and he called it continental drift. He had no idea as to how the continents moved. So I mentioned that continental drift is a great example of how the scientific method works. Wegener couldn't explain how the continents were drifting. He just knew that they were. But he didn't, and science in general, just didn't give up and throw up its hands and think, we'll never find out. They just didn't know at the time. But they didn't, first of all, completely give up. They didn't say it was impossible to know. They just didn't have the information at the time. And they certainly didn't replace the mystery of continental drift with another mystery. They didn't explain it by some other mysterious mechanism. Eventually, more information came to the fore. And this came from mapping of the seafloor, as described in section, section 27.2 of your textbook. And so by mapping the seafloor, we actually started to realize that the bottom of the sea is not just one flat expanse. It has mountains, it has valleys, just like the continents do. Now, why is that? Harry Hess is described on page 642, and he came to understand that the Earth is constantly creating new crust. The seafloor is not permanent. It's constantly being renewed at places called mid-ocean ridges, where new crust is being created. And by and he was one of the folks that actually mapped out the mid-ocean ridges and the trenches. And he realized mid-ocean ridges are where crust is being formed. Oceanic trenches are where crust is being destroyed. And so you have a very dynamic, a lot of motion going on. This could be the mechanism that drives continental drift. The fact that continents don't just stay in one place, they move around. Why is that? Because there's constantly new crust being created and new crust and crust being destroyed, old crust being destroyed. And again, scientists continue to then build evidence to support this new hypothesis. So now this was kind of a shift of things. It was no longer being called continental drift. We're actually realizing, okay, we've got these plates that are moving around. The continents just happen to be sometimes on these plates. And so the theory of plate tectonics came to be. And one of the supporting pieces of evidence is magnetic studies. So it turns out that the ocean floor records the direction of the Earth's magnetic field when new crust is being formed. So as this new crust forms at the Earth's at the ocean floor, at these mid-ocean ridges, the rocks cool, and essentially the direction of the Earth's magnetic field is essentially set in stone, locked in. And that crust then moves away from the mid-ocean ridge. A new crust is formed, and the magnetic field is again recorded whenever those rocks are formed. And we see these stripes. We see that there's been reversals of the Earth's magnetic field over time as new crust has been created. What's cool is that this theory of seafloor spreading, or this evidence of seafloor spreading, helps to not only give more support to the theory of plate tectonics, but you can also determine the rate of seafloor spreading. So that by knowing how fast these crust is being created today, we can actually then kind of wind the film backward and figure out when were the continents together. If the Atlantic Ocean is this big right now, and if it is growing at this rate, how far in the past would we have to go backward and create one big old continent? So there's a lot to be learned from this idea of seafloor spreading. And again, by measuring seafloor spreading all around the world, we essentially can come up with a nice map of the different plates. There's 8 major plates that make up the Earth's surface. The one we're of course riding on is the North American plate, but there's also other ones such as the Nazca plate, the Juan de Fuca plate, and in fact the Juan de Fuca plate and the North American plate give rise to all the action out at the San Andreas Fault in California. Okay, so the theory of plate tectonics is that we have these plates that make up the Earth's crust, and these plates are constantly in motion. So if they're going to be in motion, they're going to collide, and these collisions are not gentle sometimes. So you do wind up getting some pretty significant events, earthquakes and volcanoes and such, as a result of these interactions of plates. And you can have 3 different types of plate boundaries. You can either have divergent plate boundaries, where plates are moving away from each other. You can have convergent plate boundaries when they are crashing into each other, kind of head-on collision, or you can have transform plate boundaries in which they're kind of sliding past each other. Okay, so now you know the basics of plate tectonics and seafloor spreading, all that kind of stuff. It's a good time to take a swing at the skills test. It's actually a little game you're going to play. And one thing I'll mention is, of course, there's a video tutorial that'll help you with the interface, but also you may want to refer back to some material in Chapter 25. Remember that geologic time scale, geologic timeline. That may be useful in helping to put the different events you see in this test in the proper order. Okay, so since the plates are in motion, they really have 3 different ways that they can move past each other. So you can have a situation where this is what happens in the mid-ocean ridges. Plates are moving away from each other, and as they do, new magma comes up, creating new crust and kind of filling the void. So actually, these are areas where the plates are moving away from each other. You got new creation of new crust in the center. So not much in the way of volcanoes or earthquakes at divergent boundaries. At convergent boundaries, you do have earthquakes, you do have volcanoes, and you do have mountain building, as we're going to see. So convergent boundaries, you can actually have 2 different types. You can have oceanic boundaries. You can have oceanic continental boundaries. Now remember, oceanic crust is denser than continental crust. When they interact, when they crash into each other, it's the oceanic crust that gets sent downward, or it's called subducted. So as the oceanic crust is sent below the continental crust, that there's a lot of friction, there's heating, there's great pressure, and that actually melts some of the crust. So the crust gets destroyed and forms lava. And that lava then winds up resulting in volcanoes close to that boundary area. Another type of convergent boundary you have is continental-continental. So now you've got 2 types of crust that are essentially the same density that crash into each other. So rather than being subducted, one getting sent down, now they have nowhere to go but up. And so you have mountain building. And this is actually occurring in the Himalayas, where the Indian subcontinent has crashed into the Asian continent. And that collision of continental crust with continental crust has resulted in mountain building. Transform faults are ones where you have crust sliding past other crust. So here we got a ridge, but we've got this area here where we got a crustal plate moving past another crustal plate. That's a transform fault, and that's also an area of earthquake activity. And this is very similar to what's happening out in California. The San Andreas Fault is actually a transform boundary, and tension will eventually break up. Will build up to the point where the plates will have to slide past each other. So we have the Pacific plate going in this direction, we have the North American plate going in this direction, and therefore this transform boundary is right in here. And most of the time it's just kind of stuck, but every once in a while it frees itself up, and that's when we get earthquakes. Now, by recording the Earth's earthquake activity, it really does give a good indication as to where the plate boundaries are. Most of the earthquake activity occurs along plate boundaries. We can see how the Earth is kind of divided up into these different plates. Now, there are some earthquakes that occur in the middle of plates, such as the New Madrid plate, or the New Madrid earthquakes that I had mentioned at the beginning of this module. Those are called intraplate, so they are within or inside of a plate. So plate tectonics really doesn't account for those earthquakes, but different mechanisms, different faults that occur even within a plate can give rise to other earthquakes. But the majority of the earthquakes occur along plate boundaries according to the theory of plate tectonics. All right, you're going to get a chance to learn about the Earth's earthquakes using this world seismicity mapper. That is going to be part of your lab activity for this module. So it's somewhat involved, and so I encourage you to, again, watch the video. It'll help you to set up the simulation properly so you can come up with the proper results. Okay, because of the motion of the Earth's plates, you do get some stresses that build up. Sometimes the release of that stress is dramatic in the sense of earthquakes being the result, but you can also have just folding and pushing of rock, which is, I know, it's kind of hard to think about when we talk about the pressures involved. Sometimes you can have the folding of rock, and that depends upon the nature of the stress. So when you have pushing together of pieces of crust, you have what's called compressional stress. When you're pulling apart, it's called tensional, and then sometimes you have kind of a combination or a sliding, and that's called shear stress. And so again, depending upon the conditions, you can either have deformation that will allow the rock to return to its original shape, or it can be plastic. It can kind of just change shape relatively gently, or you can have brittle breaking of rock. Now, when you do have a compressional type stress, you can wind up with folded portions of the Earth's crust, and quite often you'll see these in like rock outcroppings. If you ever drive along a highway that's been cut out of a mountain, and you see the layers of rock, you'll see that sometimes there's folding that's happened, and that is they can be called synclines and anticlines. These areas where the folding has occurred. And so an anticline is essentially a hump, and a syncline is like a little valley. And again, your oldest layers are going to be your deepest layers are always going to be your oldest ones. Okay, so now when you have a fault, when you have areas of crust that show some layering, and you see that the layering has shifted, that means there's been a fault there. And so when you see that, you have quite often you'll see in an outcropping there might be like a little line here, and sometimes the layers have shifted either up or down, something of the sort. If you can hang a lantern from one side, that's called the hanging wall, and if you could walk on the other side, that's called the footwall. So here's an example of a reverse fault. In a reverse fault, it's the hanging wall that moves up relative to the footwall, which has moved down. So here we can see this is evidence of a reverse fault, because these layers, you can see where the layers match up, but obviously they're not in the same position. That means that your hanging wall has moved up with respect to the footwall. That's called a reverse fault. In a normal fault, it is the footwall that has moved up. So notice the footwall has moved up here compared to the hanging wall. You can see this gray, that gray layer is the same as this gray layer. They're the same age, they should be together, and yet they're not. That's because something has happened that has caused the footwall to move up and the hanging wall to move down. Now in this case, the crust is kind of pulled apart, and therefore this one has slipped down, but it's a normal fault. And then finally, another type is a shear kind of motion, where rock is slipping past each other. That's called a strike-slip fault. So there's very little vertical displacement. One side is not going up, one side is not going up. They're just kind of sliding past each other, something that's seen out in California at the San Andreas Fault. Okay, as we've already talked about to some extent, earthquakes are the result of actual, breaking of rock. When the stress becomes so great and the strain gets so great that rock just kind of gives way and slides past each other or collides into each other, you wind up with an earthquake. An earthquake is measured in using what's called the Richter scale, and there's details about the Richter scale there in chapter 26. Every once in a while, you can have an earthquake that occurs in the ocean, and when it does, huge amounts of water get pushed and winds up resulting in a tsunami. Sometimes it's called a tidal wave, but a tsunami is just a result of an earthquake that has occurred in the ocean. Okay, so now that you are well versed in plate tectonics, continental drift, earthquakes, etc., try your hand at the readiness assurance test at the end of chapter 26. Here are your answers. And also here's a look at the answers from the readiness assurance test of chapter 27.